Hello. Okay. Hello. My name is Cong Wei. I'm a postdoc associate working at the Institute for System Research. My supervisor is Dr. Paley. My topic today is distributed spacing control for multiple buoyancy-controlled underwater robots. This research is the control part of our current work, which is finding a way for a distributed system to track and observe an underwater biology system named the scattering layer. Given the underwater flow velocity and the dynamics of the scattering layer, our distributed system can achieve desired formation while tracking the scattering layer by the control algorithm. The scattering layer is a layer in the ocean consisting of a variety of marine animals. It can be seen to rise and fall each day in keeping with the diel vertical migration. It is the largest ecosystem on this planet in terms of biomass. So it attracts attention from oceanographers and underwater engineering researchers. Importance of the scattering layer in global carbon cycle is another reason that we need to investigate it continuously. Other motivation includes military purpose, since the scattering layer is always appears as a false sea floor from sonar. In our research, DriftCam, which is a buoyancy-controlled underwater robots, is applied to perform the task. Currently, a DriftCam uses optical camera with limited perception range to observe its ambient environment. Considering the physical scale, and the motion style of the scattering layer, it is reasonable to deploy a multi-agent network of DriftCam for this task. Given the ocean flow field and the dynamics of the scattering layer in horizontal and vertical space, our goal is to have any DriftCam achieve the distancing D with its immediate neighbors while tracking the depth of the scattering layer. For simplicity here, the flow field is modeled as a shear flow, and the depth dynamic of scattering layer is considered as a harmonic oscillation. Both the DriftCam and the scattering layer bear the flow velocity in horizontal direction. The control input hinges on the difference between drag force and the buoyancy, which can be tuned by changing the volume of external bladder. One technique that we apply here is the backstepping method. It is basically designing the control force based on the result of W, which denotes the desired vertical velocity. What I'm trying to say is that once we have known what the W looks like for achieving our control objective, we can then use this method to derive U. So now let's pay attention to W, which has two tasks. One is to have equal distancing, and the other is to realize depth tracking. For the first task, we derived a potential-based controller constructed on the horizontal distance between the DriftCam and their immediate neighbors within each one's perception range. Well, the tracking is achieved by the feedback controller given information of the depth and the vertical velocity of the scattering layer. Because of the time limit, I just briefly introduced the proof. We first transferred the dynamics of the DriftCam network to a new coordinate centered at the mass center of the network. We can show that the potential does not change for this transformation. With the coordinate transformation, the task of tracking is divided into two steps, where the first is to achieve the same depth for the network, and the second is the depth tracking between the mass center and the scattering layer. Once we have the desired vertical velocity, we can design the force controller by backstepping method, which is not talked in detail here. Here, 10 DriftCam is released, and we can see that at the end, they achieve equal distancing and converge to the depth of the scattering layer. The time of this process depends on the horizontal flow velocity. actually we can achieve different configurations given the requirement of the task. We are currently trying to design a flow estimator through estimating the drift cams relative motion to their neighbors. As I mentioned, our ultimate goal is to observe the motion of the scattering layer, which can be quantified as a density field of the ocean organisms. So we are also trying to achieve this goal by estimating the density evolution within the scattering layer. This research is supported by Army Research Laboratory, and the control algorithm is going to be presented at WIFR conference. The research provides a new perspective on taking advantage of environmental flow fields to facilitate formation control for long endurance multi-agent system with limited onboard actuation. The result can be applied to monitoring other targets, both underwater and above the surface. Thank you very much.